Loads that push or pull a structure sideways are called lateral loads. In most cases, those loads act as pressures on the exterior of the structure. For analysis, we need to determine how those loads move through the structure. For load to transfer, there must be connection between pieces of the structure. That probably sounds obvious, but whether two pieces of the structure are connected is not always obvious. Consider this wall being constructed. From a distance, it looks like the wall is right up against the square steel column. But look here. The wall actually attaches to the metal roof deck, which extends a bit past the column. This photo shows the deck extended beyond the column a bit more clearly. So in the case of this building, some of the wind acting on the walls gets carried down to the foundation, and the rest travels up to the roof deck. This is the most common situation for buildings. But some walls have more complex load paths. For example, consider this large wall of glass called a curtain wall. The small strips of metal holding each pane of glass are called mullions. As wind presses on the glass wall, it is similar to gravity load on a floor system. The pressure gathers on the mullions using two-way action. These horizontal members are a bit thicker and are continuous across the wall. So the smaller mullions transfer their load to these larger mullions, and these larger mullions deliver their load to these vertical trusses. So everywhere a larger mullion attaches to the truss, wind causes a point load on the truss. The truss then sends some of the load to the foundation at the bottom and to the connection at the top. The tops of these two vertical trusses connect to this large truss running parallel to the wall. That means these vertical trusses push sideways on this large truss. The large truss is touching these small joists and this other large truss. When the load path has options, stiffness attracts load. Since this large truss is much stiffer in the wind direction than these joists, the load from the large outer truss is drawn to the large truss parallel to the wind. That large truss is attached to the metal deck roof, so the wind load transfers from the truss into the deck. For buildings, lateral pressure almost always gathers at the roof and floor levels. As we saw in the two examples, the path to get there might be simple or more complex, but the lateral load still ends up in the roof and floor diaphragms. For a building like this, the wall, which has not yet been added in this photo, will send lateral pressure to the different floor diaphragms using one-way action. As a result, the lateral pressure on the exterior wall will become a distributed load along the edge of each floor diaphragm. Bridges operate the same way, but tend to be a bit simpler because there is typically only one diaphragm, the deck. Lateral pressure, due to wind or flood load, for example, converts to distributed load along the edge of the deck. So regardless of whether we are analyzing a building or a bridge, the lateral load almost always gathers along the diaphragms. So how does the load get from the diaphragms to the foundations? Lateral load resisting elements. Section 1.6 covers how to identify those elements, so for now, we just need to know they exist. Consider this simple structural system: a roof diaphragm supported only around the edges by structural walls. The lateral load on the edge of the diaphragm pushes the diaphragm, and the lateral load resisting elements push back to keep it in equilibrium. Newton's third law says that the effect on the lateral elements is equal and opposite. So we can draw an idealized elevation of one wall, and the lateral load effectively becomes a point force. Our objective at this point is to get these idealized point forces on the lateral load resisting elements. We cover how to analyze the lateral elements in later chapters.